Containers have become one of the most popular concepts used in IT and software industry in the last 5 years. Since the introduction of Docker, containers have evolved to a larger ecosystem that include many tools and technologies, including Docker and Kubernetes. Before we go into too much detail, let's look at why containers have become so popular and how they're used. First off, containers aren't a new topic. They've existed for a number of years and have taken many forms before the creation of Docker, as you can see here. In general, a container is defined as a collection of software processes unified by one namespace, with access to an operating system kernel that it shares with other containers, and little or no access between them. Docker modifies this definition by saying that a container is a runtime instance of Docker images that contain three things: a Docker image, an execution environment, and a standard set of instructions. For those coming from an object-oriented world, you can use the analogy of classes and objects, where a container is an object and the class is a Docker image. While Docker has many products and solutions, the core pieces of the ecosystem are the Docker engine and the Docker store, sometimes referred to as the Docker hub. The Docker engine is comprised of runtime and packaging tools and is required to be installed on the hosts that run Docker. The Docker store is an online cloud service where users can store and share their Docker images. One question that comes up a lot is, what is the difference between a container and a virtual machine? Containers might look like a VM, but these are two distinct technologies. In a VM, each virtual machine includes many applications, all the necessary binaries and libraries that would exist on the OS, and the entire guest operating system to interact with them. On the other hand, a container will include the application and all of its dependencies, but will share the kernel with the other containers. It is not tied to any specific infrastructure other than having the Docker engine installed on its host. It'll run an isolated process in the user space on the host operating system. This allows containers to run on almost any computer, infrastructure, or cloud. From a high level, containers provide benefits to both developers and DevOps folk alike. Developers like them because it's easy to create applications that are portable and packaged in a standard way. They also make the process of deployment very easy and repeatable. Testing, packaging, and integrations can be automated in an easier way than before. Containers support newer microservices architectures, which fit better from a developer mindset. And finally, containers help alleviate platform compatibility issues. From a DevOps standpoint, using containers simplifies release management. Deployments become much more reliable, which improves the speed and frequency of releases. The application lifecycle is consistent. They can be configured once and run multiple times, making the process more repeatable and efficient. Environments can be made more consistent. No more process differences between the dev, staging, and production environments. Scaling applications also becomes a lot simpler. Containers take a few seconds to deploy to a host, which makes the process of adding extra workers easier, and the workload can grow and shrink more quickly for on-demand use cases. One of the biggest value adds of using container technologies in an enterprise is that developers and DevOps team now have a common language to collaborate. Both sets of teams can describe their needs and architectures in terms of containers, using the same vocabulary for dev and deployment. Issues that come up in production by a DevOps team can be easily communicated back to the development team. The dev team can isolate and debug specific issues to a container level, eliminating problems relating to differences in hosts or runtime issues with applications. With all the benefits that containers bring to the table, it's no wonder that there's such a dramatic increase in their use. A Forrester survey conducted in 2017 indicated that organizations expect the number of containerized apps will rise by 80% in 2019. The white paper is a great read and talks about some of the most prominent use cases of containers in different sized orgs. Organizations use containers to build applications to incorporate a microservices-based architecture. Newer applications are built with a microservices mindset, using containers underneath to realize this. And legacy applications are shipped as containers to fit the microservices mold as well. Finally, containers assist with code agility and help you build a continuous integration or continuous deployment pipeline. This use case really pushes an IT team to develop, test, and deploy applications faster in a more automated fashion. Hopefully by now, it's clear why enterprises have started to adopt containers in such a big way. Now that we understand what containers are all about, let's see where Kubernetes plays a role. Now let's talk about Kubernetes, the most popular open source container orchestrator available today. The adoption of Docker has really taken off in the last few years. Per the 2017 Docker survey by Datadog, Docker adoption was up 40% in Datadog's very large customer base. Additionally, the 2017 Docker usage report conducted by Sysdig stated that the median number of containers running on a single host is about 10. All this data begs an important question. How do you manage all these running containers on a single host, and more importantly, across your whole infrastructure? This is where the idea of container orchestrators come in. Container orchestration solves the problem of deploying multiple containers, either by themselves or as a part of an application, across many hosts. From a high level, some of the features required are the ability to provision hosts, start containers on a host, be able to restart failing containers, have the ability to link containers together so that they can communicate with their peers, expose required containers as services to the world outside the cluster, and scaling the cluster up or down. There are a few solutions in the container orchestration space, and we'll cover more of these later on. Kubernetes is an open source platform designed to automate the deployment, scaling, and operation of containers. The real goal of the platform is to foster an ecosystem of components and tools that relieve the burden of running applications in public and private clouds. Kubernetes, often called K8s or Kubernetes, is an open source platform that started at Google. Internally, all of the Google infrastructure relies on containers and generates more than 2 billion container deployments a week, all powered by an internal platform called Borg. Borg was the predecessor to Kubernetes, and the lessons learned from developing Borg over the years has become the primary building blocks in the development of Kubernetes. Simply put, using Kubernetes in your infrastructure gives you a platform to schedule and run containers on clusters of your machines, whether it's on bare metal, virtual machines, in a private data center, or in the cloud. This means no more golden handcuffs and opens up opportunities to have hybrid cloud scenarios for your folks migrating towards the cloud. Because Kubernetes is a container platform, you can use Docker containers to develop and build applications, and then use Kubernetes to run these applications in your infrastructure. It's important to note that you don't have to use Docker containers. You can use Rocket by CoreOS or other container platforms. However, most users in the container ecosystem use Docker containers, so we'll use Docker for this course. There are many companies that use Kubernetes today for different use cases. I'll discuss a few of these to document common ways companies are using Kubernetes. Box has been moving towards a microservices architecture for their infrastructure and became an early adopter. Kubernetes has provided Box's developers a common development platform to build microservices. Also, since Kubernetes can run on bare metal just as well as the cloud, Box could create a migration strategy to Google Cloud. It could also use the same tools and concepts to run across their existing data center and the new Google Cloud. Pokemon Go. When a game has the motto, "Gotta catch them all," it retrospectively comes as no shock that as soon as it launched, within half an hour, traffic surged and crashed all of Pokemon Go servers. To keep up with traffic, Niantic got help from teams at Google to move Pokemon Go to the Google Container Engine. To date, Pokemon Go is the largest Kubernetes deployment on the Google Container Engine. Due to the scale of the cluster and accompanying throughput, a multitude of bugs were identified, fixed, and merged back to the Kubernetes codebase. eBay was an early adopter of OpenStack and used OpenStack as the platform to run their virtual machines. However, as the infrastructure grew, developers found it easier to manage and deploy containers as opposed to working with VMs or applications directly on OpenStack. As a result, eBay moved to use the Kubernetes platform from OpenStack Magnum. This allowed the company to manage the infrastructure more easily and allowed their developers to continue to be agile and productive. In the next section, we'll take a look at why Kubernetes is so effective and why people like it so much. To kick off this section, I wanted to give you my favorite definition of Kubernetes that I've heard. It's by Joe Beda, who's one of the original Kubernetes developers and has done some really cool things in the Kubernetes and cloud-native landscape. He said, "Kubernetes is an open source project that enables software teams of all sizes, from a small startup to a Fortune 100 company, to automate deploying, scaling, and managing applications on a group or cluster of server machines." These applications can include everything from internal-facing web applications, like a content management system, to marquee web properties like Gmail, to big data processing. I really like this quote because I think it encompasses everything when I think about Kubernetes. In this section, we'll break down the different features of Kubernetes that make it a great platform to manage your containerized applications. Let's take a look at some of these. First up, multi-host container scheduling. This feature is handled by the kube scheduler, which assigns containers, also known as pods in Kubernetes, to nodes at runtime. It accounts for resources, quality of service, policies, and user specifications before scheduling. Scalability and availability. The Kubernetes master can be deployed in a highly available configuration. Multi-region deployments are also available as well. From a scalability perspective, in Kubernetes 1.17, the architecture supports up to a 5,000 node cluster and can run up to a maximum of 150,000 pods. The pods can also be horizontally scaled via an API. Flexibility and modularization. Kubernetes has a plug-and-play architecture that allows you to extend it when you need to. There are specific add-ons for network drivers, service discovery, container runtime, visualization, and command. If there are tasks that you need to perform for your environment specifically, you can create an add-on to suit your needs. Two features that allow Kubernetes clusters to scale are registration and discovery. New worker nodes can seamlessly register themselves with the Kubernetes master node. Kubernetes also includes service discovery out of the box. Service discovery allows for automatic detection of new services and endpoints via DNS or environment variables. It also allows for persistent storage, which is a much requested feature when working with containers. Pods can use persistent volumes to store data, and the data is retained across pod restarts and crashes. Application upgrades is one area where the Kubernetes project has done a lot of pioneering work. Application upgrades are supported out of the box, as well as rollbacks. When it comes to Kubernetes maintenance and upgrades, Kubernetes features are always backward compatible for a few versions. All APIs are versioned, and when upgrading or running maintenance on a host, you can unschedule the host so that no deployments can take place on it. Once you're done, you can simply turn the host back on and schedule deployments or jobs. In terms of logging and monitoring, application monitoring or health checks are also built in. TCP, HTTP, or container exec health checks are available out of the box. There are also health checks to give you the status of the nodes and failure monitored by the node controller. Kubernetes status can also be monitored via add-ons like the Metric Server, cAdvisor, and Prometheus. And lastly, you can use the built-in logging frameworks, or if you choose, you can bring your own. Management of secrets. Sensitive data is a first-class citizen in Kubernetes. Secrets are mounted as data volumes or environment variables. They are also specific to a single namespace, so aren't shared across all applications. Now that you know what Kubernetes is all about, it's time to discuss other platforms that are similar. We're in the software world after all, and there are many ways to solve the same problem. Before we begin, I need to get something off my chest. Container orchestration is a very complicated topic. When containers first became a hot topic, a lot of folks, enterprises included, were building their own orchestration tools in-house because the landscape was very nascent at that time. Eventually, almost every company ended up moving to one of the solutions I'll talk about in this chapter. So in short, don't build your own orchestrator. You'll only regret it and end up moving to something else anyways. The cloud-native landscape today is typically based around Kubernetes, but there are also other technologies and architectures that are popular. Mesos and Rancher are popular from a container perspective, and serverless technologies are also gaining popularity for application modernization. There are also cloud-specific technologies like Amazon EC2 Container Service or Google Anthos that are technologies built specifically for those ecosystems, but we won't spend too much time comparing them in this section. We talked about Kubernetes, so let's take a look at some of its competitors. Mesos is written in C++, with APIs in Java, C++, and Python. It has a distributed kernel where many machines act as one logical entity. The Marathon framework in Mesos is used to schedule and execute tasks, And finally, Mesos has a more complex architecture compared to other technologies like Docker Swarm, for example. Typical users of Mesos are larger enterprises that require a lot of compute or job or task-oriented workloads. Mesos is often used by companies that have to perform big data jobs. It's driven by developers rather than operations, but requires an ops team to manage the tool. Rancher is a full-stack container management platform. It allows you to install and manage Kubernetes clusters easily, whether on-premise or in the cloud. It was an early player in the container ecosystem and had orchestration concepts even before they became a hot topic. It has a great user interface and API to interact with clusters and provides enterprise support for its tooling. I've seen a lot of folks use Rancher, from small teams to large enterprises. Folks that like to use Rancher really enjoy the user interface and APIs, and allows them to manage their infrastructure very effectively. This chart plots the number of hosts and containers versus the size of the development team. If you're running a lean shop, you should consider some of the solutions on the left. If you're a larger enterprise, you probably lean towards one of the more feature-rich solutions on the right. Let's take a look at the entire Kubernetes cluster architecture. As you can tell, it's got a lot of boxes and even more arrows. Let's break this down and build it back up. First up, we have the master node. This guy is responsible for the overall management of the Kubernetes cluster. It's got 3 components that take care of communication, scheduling, and controllers. These are the API server, scheduler, and cluster manager. The Kube API server, as the name states, allows you to interact with the Kubernetes API. It's the front end of the Kubernetes control plane. Next up, we have the scheduler. The scheduler watches created pods who do not have a node assigned yet and assigns the pod to run on a specific node. The controller manager runs controllers. These are background threads that run tasks in a cluster. The controller actually has a bunch of different roles, but that's all compiled into a single binary. The roles include the node controller, who's responsible for the worker states, the replication controller, which is responsible for maintaining the correct number of pods for the replicated controllers, the endpoint controller, which joins services and pods together, service account and token controllers that handle access management. Finally, there's etcd, which is a simple distributed key value store. Kubernetes uses etcd as its database and stores all cluster data here. Some of the information that might be stored is job scheduling info, pod details, state information, etc. And that's the master node. You interact with the master node using the kubectl application, which is the command line interface for Kubernetes. Kubectl is also called Kubectl in some instances, but I'm going to say kubectl for the rest of the course. Kubectl has a config file called the kubeconfig. This file has server information as well as authentication information to access the API server. We wouldn't get anywhere without worker nodes though. These worker nodes are the nodes where your applications operate. The worker nodes communicate back with the master node. Communication to a worker node is handled by the kubelet process. It's an agent that communicates with the API server to see if pods have been assigned to the nodes. It executes pod containers via the container engine. It mounts and runs pod volumes and secrets, and finally is aware of pod and node states and responds back to the master. It's safe to say that if the kubelet isn't working correctly on the worker node, you're going to have issues. As I mentioned before, Kubernetes is a container orchestrator, so the expectation is that you have a container-native platform running on your worker nodes. This is where Docker comes in and works together with Kubelet to run containers on the node. You could use alternate container platforms as well, like CoreOS Rocket, but not a lot of folks do this anymore. The next process I'll talk about is the kube proxy. This process is the network proxy and load balancer for the service on a single worker node. It handles the network routing for TCP and UDP packets and performs connection forwarding. Alright, we're on home stretch. Having the Docker daemon allows you to run containers. Containers of an application are tightly coupled together in a pod. By definition, a pod is the smallest unit that can be scheduled as a deployment in Kubernetes. This group of containers share storage, Linux namespace, IP addresses, amongst other things. They are also co-located, hence share resources that are always scheduled together. Once pods have been deployed and are running, the kubelet process communicates with the pods to check on state and health and the kube proxy routes any packets to the pods from other resources that might be wanting to communicate with them. Worker nodes can be exposed to the internet via a load balancer, and traffic coming into the nodes is also handled by the kube proxy, which is how an end user ends up talking to a Kubernetes application. That's the entire Kubernetes architecture. In this section, we'll take a deeper look at some of the components and concepts that one uses on worker nodes to build applications in Kubernetes. This is another way to look at the same architecture, but from a cluster perspective. From this perspective, the master is responsible for managing the cluster. It coordinates all the activities in the cluster and communicates with the nodes to keep Kubernetes and your applications running. The node serves as a worker machine in the Kubernetes cluster. One important thing to note is that this node can be a physical computer or a virtual machine. The node has the following requirements. Each node must have a kubelet running, container tooling like Docker, a kube proxy process running, and a process like supervisor-d so it can restart components. I'll go over more details on the specifics of these components in a later section. One thing to note is that if you're using Kubernetes in a production-like setting, it's recommended that you have at least a 3-node cluster. For this course, we will use Minikube, which is a tool to run Kubernetes locally. It's a lightweight Kubernetes implementation that creates a virtual machine on your local box and deploys a simple cluster containing one single node. In the Kubernetes model, a pod is the simplest unit that you can interact with. You can create, deploy, and delete pods, and it represents one running process in your cluster. A pod contains the following things: your Docker application container, storage resources, a unique network IP, and options that govern how the container should run. In some scenarios, you can have multiple Docker containers running in a pod, but a pod represents one single unit of deployment, a single instance of an application in Kubernetes that's tightly coupled and shares resources. Pods are designed to be ephemeral, disposable entities. I never create pods just by themselves in a production application. I only do that when I need to test whether the underlying containers actually work. Pods also don't self-heal. If a pod dies for some reason, it will not be rescheduled. Also, if a pod is evicted from a node because of lack of resources, it will not be restarted on different, healthier nodes. There are higher-level constructs to manage and add stability to pods called controllers. So pro tip, don't use a pod directly. Use a controller instead, like a deployment. Through its lifecycle, a pod has the following states: pending, which means that the pod has been accepted by the Kubernetes system, but a container has not been created yet; running, where a pod has been scheduled on a node and all of its containers are created and at least one container is in a running state; succeeded, which means that all the containers in the pod have exited with an exit stat of 0, which indicates successful execution and will not be restarted; a failed state, which means all the containers in the pod have exited and at least one container has failed and returned a non-zero exit status; or my favorite, which is the crash loop backoff. This is where a container fails to start for some reason, and then Kubernetes tries over and over and over again to restart the pod. Before we dive into the details, it's good to understand what problems controllers actually help us solve. These are application reliability, where multiple instances of an application running prevent problems if one or more instances fails; scaling, when your pods experience a high volume of requests, Kubernetes allows you to scale up your pods, allowing for a better user experience; and finally, load balancing, where having multiple versions of a pod running allow traffic to flow to different pods and doesn't overload one single pod or a node. I'll cover the following kinds of controllers: replica sets, deployments, daemon sets, jobs, and services. First off, replica sets. A replica set has one job. It ensures that the specified number of replicas for a pod are running at all times. If the number of pods is less than what the replica set expects, for example, when a pod might have crashed, the replica set controller will start up a new pod. However, you can't actually declare a replica set by itself. You'll need to use it within a deployment. So let's look at what that is. A deployment controller provides declarative updates for pods and replica sets. This means that you can describe the desired state of a deployment in a YAML file, and the deployment controller will align the actual state to match. Deployments can be defined to create new replica sets or replace existing ones with new ones. Most applications are packaged as deployments, so chances are you'll end up creating deployments more than anything else. Essentially, a deployment manages a replica set, which in turn manages a pod. The benefit of this architecture is that deployments can automatically support a rollback mechanism. A new replica set is created each time a new deployment config is deployed, but it also keeps the old replica set. This allows you to easily roll back to the old state if something isn't quite working correctly. Deployment controllers and objects are higher-level constructs that were introduced to solve specific issues. Pod management, where running a replica set allows us to deploy a number of pods and check their status as a single unit. Scaling a replica set, which scales out the pods and allows for the deployment to handle more traffic. Pod updates and rollbacks, where the deployment controller allows updates to the pod template spec. This creates a new replica set and deploys a newer version of the pod. Also, if you don't like what you see in the newer version of the pod, just roll back to the old replica set. Pause and resume. Sometimes we have larger chain sets or multiple updates that need to happen to a deployment. In these scenarios, we can pause a deployment, make all the necessary updates, and then resume the deployment. Once the deployment is resumed, the new replica set will be started up and the deployment will update as expected. Please note that while the deployment is paused, it means that only updates are paused, but traffic will still get passed to the existing replica set as expected. And finally, status. Getting the deployment status is an easy way to check for the health of your pods and identify issues during a rollout. We'll go deeper into how deployments work in the demo section of this course. You might have come across replication controllers if you search for Kubernetes controllers. This was an early implementation of replica sets, but it has since been replaced by deployments and replica sets. So in short, use deployments and replica sets instead. Next up, we have daemon sets. Daemon sets ensure that all nodes run a copy of a specific pod. As nodes are added or removed from the cluster, a daemon set will add or remove the required pods. Deleting a daemon set will also clean up all the pods that it created. The typical use case for a daemon set is to run a single log aggregator or monitoring agent on a node. A job, as the name suggests, is basically a supervisor process for pods carrying out batch processes to completion. As the pod completes successfully, the job tracks information about the completion state of the pod. Jobs are used to run individual processes that need to run once and complete successfully. Typically, jobs are run as a cron job to run a specific process at a specific time and repeat at another time. You might use a cron job to run a nightly report or database backups, for example. A service provides network connectivity to one or more pods in your cluster. When you create a service, it's assigned a unique IP address that never changes through the lifetime of the service. Pods are then configured to talk to the service and can rely on the service IP on any request that might be sent to the pod. Services are a really important concept because they allow one set of pods to communicate with another set of pods in an easy way. It's a best practice to use a service when you're trying to get two deployments to talk to each other. That way, the pod in the first deployment always has an IP that they can communicate with, regardless of whether the pod IPs in the second deployment changes. For example, when your front-end deployment needs to call the back-end deployment, you want to address the back-end with a service IP. Using the back-end pod IP is a bad choice here because it can change over time and will wreak havoc for your application. A service provides an unchanging address so that the front-end pods can effectively talk to them at all times. There's a few kinds of services that you can use. Internal services, where an IP is only reachable from within the cluster. This is the cluster IP in Kubernetes speak. Then, there are external services, where services running web servers or publicly accessible pods are exposed through an external endpoint. These endpoints are available on each node through a specific port. This is called a node port in Kubernetes speak. And finally, we have the load balancer. This is for use cases when you want to expose your application to the public internet. It's only used when you are using Kubernetes in a cloud environment backed by a cloud provider such as AWS. The last must-know concept to build applications are labels, selectors, and namespaces. These constructs allow us to annotate and organize our applications so that when we have a lot of them, Kubernetes operators still understand what's going on holistically. Labels are key value pairs that are attached to objects like pods, services, and deployments. Labels are for us, the users of Kubernetes, to identify attributes for objects. Typically, labels are used to organize clusters in some meaningful way. They can be added at deployment time or later on and changed at any time. Label keys are unique per object. Here are some examples of labels we might use. We might have a release label that has stable or canary deploys. We could have environment labels that specify the environment, such as dev, QA, production, etc. Or perhaps tier labels to signify that something is a front-end or a back-end tier. As you can tell, labels are very specific to your use case, and they are built for users. So think about what your environment looks like and how you want to organize your applications, and then get your label maker out. By themselves, labels aren't really that powerful. But when you add selectors, you introduce a very powerful feature. With labels and selectors, you can identify a specific set of objects. There are two kinds of selectors, equality-based and set-based. Equality-based selectors include the equals and not equals, where the equals represents equality, where two labels or values of labels should be equal. Not equal represents inequality. This means that the values of the labels should not be equal. Next, we have set-based selectors that include in, not in, and exist operators. The in operator specifies that the value should be in a set of defined values. The not in operators specify that the value should not be in a set of defined values. And finally, the exist operator is used to determine whether a label exists or not. Labels and label selectors are typically used with the kubectl command to list and filter objects. We'll look at examples of how to use labels and selectors later on in the demo section of the course. And finally, we have namespaces. Unlike labels and selectors, the namespace concept is a feature of Kubernetes that allows you to have multiple virtual clusters backed by the same physical cluster. Namespaces are a great concept to use for large enterprises, where there are many users and teams, and you want to give access to different teams, but at the same time have a rough idea of who owns what in the Kubernetes environment. For example, if you have a big e-commerce company, you might have a namespace for your catalog team, cart team, and order status team to run their different applications. It's also a great way to divide cluster resources between multiple users, and this can be done using resource quotas. Namespaces provide scope for names. Names of resources like deployments and pods must be unique within a namespace, but not necessarily across separate namespaces. So in our example, the catalog team and the cart team can have an application named authentication in their own namespaces. When you launch Kubernetes, there is a default namespace where all our objects get placed, but you are allowed to create new namespaces as and when you wish. Also, you'll notice that when you install a newer application in Kubernetes, they'll typically install in a brand new namespace so that they don't interfere with your existing cluster and cause confusion. The Kubelet is the Kubernetes node agent that runs on each node. It has many roles. It communicates with the API server to see if pods have been assigned to the nodes. It executes the pod containers via the container engine. It mounts and runs pod volumes and secrets. It executes health checks and is aware of pod and node status, and reports that back to the API server. The kubelet works in terms of a pod spec, which is just a YAML file that describes the pod. The kubelet takes a set of pod specs that are provided by the Kube API server and ensures that the containers described in those pod specs are running and healthy. It's important to note that the kubelet only manages containers that were created by the API server and not any other containers that might be running on the node. You can also manage the kubelet without an API server by using an HTTP endpoint or a file, but that's beyond the scope of this course. The network proxy is called the kube proxy. This is another process that runs on all the worker nodes. The kube proxy reflects services that are defined in the API on each node and can do simple network stream or round-robin forwarding across a set of backends. Service cluster IPs and ports are currently found through Docker link compatible environment variables specifying ports opened by the service proxy. The kube proxy has three modes: the user space mode, IP tables mode, and IPVS mode, which is an alpha feature in Kubernetes 1.8. The user space is the most common mode. These modes are important when it comes to using services. Services are defined against the API server. The kube proxy watches the API server for addition and removal of services. For each new service, kube proxy opens a randomly chosen port on the local node. any connections made to that port are proxied to one of the corresponding backend pods. Before we get Kubernetes installed, we need to have Docker and a hypervisor installed. If you head on over to the Docker website, and then go to Products, select Docker Desktop. You'll notice that it's cross-platform, so no matter whether you're on PC, Mac, or Linux, you're covered. I already have it installed on my Mac. If you don't have it installed, you'll want to follow the links here to do so before moving on. Let me switch over to the terminal and verify that it's indeed running. I'll type docker version, and here I notice that I'm running the client version of Docker Engine Community, version 19.03.5, and from a server perspective, I'm running Docker Engine Community, version 19.03.5. Your version might be different, and that's okay. As long as you're at least running 19.03.5, things should work for this course. Our next prerequisite is a hypervisor. If you're not familiar, a hypervisor is an app that lets you run and manage virtual machines. One cross-platform solution for this is called VirtualBox. Here on my machine, I've already got it installed. Installation is pretty straightforward. Just download the installer and run it. If you don't already have it installed, please do so now before moving on. So now let's go ahead and install Kubernetes. Since I'm doing this on the Mac, I'm going to click Install Kubectl on the Mac OS. I can download the latest release, copy that, and I can go to my terminal window, paste that command, and this is just basically pulling the latest version of Kubectl from the repository. That looks like it's done. Go back to the script here, make it an executable, move it to the right path. The first time you do this, it might ask you for your password, and that's expected. And let's actually test to make sure that we have the right version. So Kubectl version client, this is major version 1, minor version 18, so we're running version 1.18. Looks good. The next part is installing Minikube. So that's actually on the same site. Under Tools, you can install Minikube. Once again, we're going to do this for the Mac. We've already set up Kubectl, so that looks good. And we can either use the brew install method or download the standalone binary. I'm going to do the latter. And this actually downloads the latest binary for Minikube and also chmods it as well. So go back here. And finally, we're going to move this to user local bin. All right. And we can test our cluster by doing a quick Minikube status. So it looks like everything stopped, which is what we expect. And we can do a Minikube version. And this is Minikube version 192. So we have all the tools that we need. In this scenario, I'm installing this on Windows 10 Enterprise Edition. However, you can also do this on Windows 10 Pro. The first pre-requirement we need is Docker. Let's go to the Products tab and go to Docker Desktop as a product offering. And you can see that you can get the download for Windows. Go ahead and do that. I already actually have it installed. And you can see that in Docker Desktop is up and running in the little taskbar. And in this scenario, I have Docker Desktop for Community Edition, version 2.2.05, channel stable. Let's make sure that I'm actually running this on the command line. So open up PowerShell. Run as the administrator. Let's do a Docker PS, and then a Docker version. So you can tell I'm running client version 19.03.8 and the server version also 19.03. Clear out of here. So we have Docker for desktop, and that's great. The second thing we need is Kubectl. I'm going to install and set up Kubectl. The most popular question that I get with Kubernetes surrounds how to get started and whether one can use other platforms to learn Kubernetes. I thought it would be great to clarify this for new users up front. In terms of getting your hands dirty with Kubernetes, there are actually many ways to do this. The top 4 technologies here are Minikube, Docker for desktop, Kubernetes and Docker, also known as Kind, and Kubernetes in a cloud provider. Let's see the pros and cons of these. First up, Minikube. I based this course on Minikube for a few reasons. Minikube was the first tool to be able to run a local cluster on your machine and has one of the largest special interest groups supporting it within the Kubernetes community. Last I checked, it has over 18,000 stars on GitHub and close to 500 code contributors. It supports the latest release of Kubernetes in a very timely manner, and you're not waiting too long to try out the latest version of Kubernetes locally. The user experience of Minikube is targeted for brand new users to the ecosystem and are trying to understand how everything works. It abstracts away many complexities when all you're wanting to do is to get started. One of the most powerful features of Minikube is the add-on feature, where Kubernetes tooling is bundled in and supported with Minikube, so you don't have to spend extra time learning how to install it. It's actually something we will use later on in this course to explain the Kubernetes dashboard and the metrics server. The other really popular tool for running Kubernetes is Docker Desktop. The Docker Desktop environment allows you to easily create a Kubernetes cluster from the Docker user interface. The experience for new users is great, and I'd recommend Docker for Desktop as an alternative if you're having trouble with Minikube. The one disadvantage of Docker for Desktop with respect to Kubernetes is that it tends to lag on the latest Kubernetes version release compared to Minikube. Kind, also known as Kubernetes in Docker. Kind is a popular tool in the Kubernetes ecosystem to run local Kubernetes clusters using Docker containers as nodes. Initially, Kind was created to test Kubernetes, Kubernetes features, and used to test Kubernetes in a continuous integration environment. Chances are, if you're going to be doing a lot of testing or integration work with Kubernetes, you'll want to consider Kind for your primary development environment. It works great, but probably not suited for new beginners who are trying to learn Kubernetes. And finally, Managed Kubernetes Services. Managed Kubernetes services are very popular on cloud providers today. They allow you to run clusters without having to worry about managing the actual Kubernetes control plane. Managed offerings are available on all major cloud providers today, and if you're already working in the cloud, it's something you could consider. Quick word of caution though, if you're new to Kubernetes and new to the cloud, I'd probably just stick with Minikube for this course. It can take some time to understand how to provision a cluster in a cloud environment, and you might end up spending more time getting a cluster created rather than running a hello world. To start up Minikube, you can type the command minikube start. The very first time this runs, you'll notice that this might take a little while to actually go ahead and get all of the different pre-loaded images, etc. for Kubernetes, and that's expected. Once this completes, we get a quick note saying that it's done and kubectl is now configured to use Minikube. So let's actually take a look to see whether this is up and running. I can do this by running the command kubectl get nodes. So I'm going to clear my screen and do a kubectl get nodes. And in this case, we see that we have, nodes. It's called Minikube in a ready status with roles of master. 30 seconds old because it was just created. And this is version 1.18, which is also the Kubernetes version. Next up, we're actually going to run a quick hello world to make sure everything's up and running as we expect. But first up, let's look to see what's in our cluster right now. We just created this, so there shouldn't be anything in there. To figure out what's in your cluster, you can run the command kubectl get all, returns all resources. And like I said before, not a whole lot, just the service Kubernetes with the cluster IP. It's been online for about 15 minutes or so. All right, let's go ahead and deploy our application. In order to do that, I'm going to run the command kubectl create, because I'm going to create a resource, -f, meaning file, and then hello world. And we get a deployment hello world that was created. Once again, if I run kubectl get all, I should hopefully see more resources here. And I do. I see the service that was there before, but now we have a pod of hello world with a GUID passed after that, a deployment of hello world, and also a replica set associated with that. The other things to kind of look forward to over here are the ready states. So we notice that the pod is ready to go, 1 of 1. Deployment is ready to go, 1 of 1 as well. All of these seem to have an age of 11 seconds. So in all counts, it looks like the deployment is ready to go. But how do we actually access this, right? Because this has a little web page that we want to access. How do we go about that? So in order to do that, we need to create the service construct for Kubernetes, and I can expose this deployment as a service. So in order to do that, let's clear my screen. I can run the command kubectl expose, and I'm going to expose the deployment. I need to pass the name, so we call this hello world earlier, and I'm going to expose this as a type of node port. And we'll notice here that it says service hello world was exposed. So if I take a look at the cluster again, get all, we notice that we now have 2 services, the Kubernetes one like we had before, but now hello world. It's of type node port, which is what we declared it as. Been online for 9 seconds and should be accessible on this specific port. One of the nice things about Minikube is I can run the Minikube service hello world command. And by service hello world, it should reference the hello world service we just created. Once I run this, it actually takes me to the web browser on the specific IP and port, and it brings up our little deployment exposes service, which is our little UI. You can reload this. We see the counter that keeps reloading. And one of the neat things I've done here is I can actually copy the container ID, bring this back to the terminal. And if I search for the container ID, we'll notice that it references the pod that we just have, which is great. The other thing I want to call out attention to, we kind of scrolled up a little bit too fast, but when you run Minikube service hello world, we notice we get this little table. It says, the namespace default, the application name, and the URL. So 192.168.64.2, 32.124, which is essentially what we saw over there. At the end of the last section, we had our application up and running in the web browser. But let's go ahead and understand what the basics of the application are and how this interacts with the deployments and services. So in order to do that, I'm going to go back to my terminal window. And to understand all the resources that Kubernetes has up and running, you can run the Kubernetes command kubectl get all. So this essentially returns all of the resources that we have in the cluster. So we notice that we have a pod running, we have a couple of services, the deployment that we had deployed, and the replica set as well. So let's go ahead and look at some of these in a little bit more detail to understand what's going on behind the scenes. I'm going to clear my screen, and what I'd like to do is actually look at the deployment first. And to do that, I can run the kubectl get deployment command. Instead of getting all resources, I'm just limiting this to just the deployment. So I can do that, and we'll notice that we have a specific deployment here called hello world. If I want to introspect into the hello world deployment, I can do that by running kubectl get deployment /hello world. And I want to output this as YAML. And we notice that we have some YAML that we can look at. So this is the YAML of the live running deployment that we have up and running right now. It's API version 1.0. It's of a kind deployment. There's some metadata associated with this. Scrolling down, we notice that there's an API version. Once again, it has a name of hello world. It's deployed to the default namespace. And the spec section is the section you'll end up looking at a lot when you're running these deployments. Over here, we notice that we have a replica up and running, selectors with some labels where we have a match label of hello world, a strategy for how we actually roll this out, and the template, which actually contains your spec and your containers, where you signify what image you actually have. So Karthikeyan hello world is the image that we actually have up and running. Let's do the same thing for the service. So I'll clear my screen. I can run kubectl get service, and I'm going to introspect into the hello world service here. So kubectl get service / hello world. Once again, I'm going to output this as YAML. And in fact, I'm going to clear my screen. And here we notice that we have API version 1, it's kind service, metadata once again. And in the spec section, this is where we have cluster IP, the ports, including the node port for 32124. It's linked to port 80 with a target port of 80, and we're using the protocol of TCP. So that's great. Now, in the last section, you notice that we deployed 2 artifacts, the deployment, and then we deployed the service. So I can do a cat of hello world service, and we notice that we have the spec section, node port, followed by the protocol, target port and ports, etc. So when we're running these, we can run a kubectl create -f hello world deployment.yaml. This will create the deployment. Similarly, I'm going to create the service. Service YAML. So I've created a couple of resources. So let's do get all. kubectl get all resources. Here you'll notice we have a couple of pods running. This is the one from before, 48 minutes. This is the new hello world pod from the deployment. It's running for 22 seconds. We have a new service up there called the hello world service, as well as a couple of deployments now, one that was just deployed 22 seconds ago. Now this can get a little tedious. Notice that I typed in a couple of commands, but there's a way to make this simpler. So let's take a look at the YAML file that we have in this folder. Hello world-all. And you'll notice here that this looks exactly like what we had before, in terms of we have the deployment, and then we have this 3- notation, and it looks like we have a service here. Essentially, the 3- notation allows you to add multiple files into a single file, so we can actually go ahead and execute just one file to deploy all of your artifacts. It makes life a little bit simpler than having to run a lot of deploys for many files. So I can run kubectl create -f hello world-all.yaml. And here we see we have a couple of things that ended up getting created, the deployment and the service. Let's just look at the deployments. We notice now that we have 3 deployments. The hello world, this is the one we initially had. Hello world deployment that we just deployed about 2 minutes ago. And then the hello world all deployment. Similarly, kubectl get services. We have a few more services now. The hello world that we did 15 minutes ago, the hello world service that we did a couple of minutes ago, and then the hello world all service. All of these have different ports that you can access these on because they're individual apps that are up and running, because they're individual deployments. But you get the gist that you can have one single file to deploy many things versus having multiple files to do one single thing. If I do an ls-al, you'll notice that there are 3 files with this section. The README, the hello world pod with labels.yaml, and a sample infrastructure with labels.yaml. We're going to use both of these files as sample data that we want to create deployments and services with, which are already going to have labels associated with them. So for the first section, let's actually look at the hello world pod with YAML. I'm going to vi hello world pod with labels.yaml. This is a simple pod which has some labels called env production, author Karthikeyan, application type UI, and a release version of 1.0. So I'm going to run this. kubectl create -f, and let's make sure that the pod is online. All right, sounds good. We have a hello world pod, ready status, which is in the status of running, and it's been online for 7 seconds. So we've seen this before, but how do we actually look at the labels associated with that? In order to do that, we would run kubectl get pods just like before, and then we'd add the show labels tag. As you can see, there's a new section called labels which have the application type UI, author, environment, and release version, just as we had seen in our actual file. This is how we would add labels at deployment time. You can also add labels to the running pod, because in some scenarios, you might want to tag a pod after it's been deployed. This is how we would do that. kubectl, we'd use the label construct, and our pod was called hello world. We're going to relabel the app as hello world app instead of just hello world like it was. And in order to change this, you can do an overwrite. So let's take a look again. kubectl label or kubectl get pods ---- show labels. So we rewrote this, and there we see the real value of the new label. So what happens in the scenarios where we want to delete a label? In order to do that, we can actually rerun a kubectl label. We want to relabel this pod /hello world, and we want to actually delete this label because we don't really want it anymore. So you do an app because that's the label name. And if I add a minus, we get a result saying pod hello world was labeled. So let's take a look at this again. kubectl get pods. You'll notice from before we had app hello world, and we do not have that anymore. So that's how you actually end up deleting a label or overriding it. Next up, let's talk about how we can search by labels. In order to do that, let me create some sample infrastructure for us to run. I'm going to do this with kubectl create -f sample infrastructure with labels.yaml. All this is doing behind the scenes is creating a bunch of pods that have labels associated with them. So I'm going to clear screen and do a kubectl get pods. We have some pods, and this example is a large e-commerce store that has different teams associated with different applications. For example, there's a cart application, there's a catalog, there's a home page, and a login application, ordering, etc. And it also has different tiers like dev, production, staging. Let's take a look again to see if the pods are running. It looks like all the pods are up and running. Next, let's take a look at the labels associated with them. Get pods. Great. As you can see, we have a lot of labels associated with the application. What I'm going to do is I'm going to reduce my font a little bit. Once again, we noticed that we have a lot of labels, and we've seen how we can list labels, but let's figure out how we can search for them. In order to do label searches, we want to use selectors with labels to do this. So I'm clear my screen, and we are going to look for all of our labels that are in the production environment. In order to do this, I would do a kubectl get pods, just like before. I'm going to add a selector, and I'm going to put env equals production. And our list of pods has drastically reduced, and all of the pods returned are pods that we have running in production. In fact, I'm going to do show labels here. And as you can tell, we have a cart prod and we have an env in production. And if I search for this, you'll notice that all of my labels are associated with an application that's been tagged to run in a production-like setting. All right, let's do another example. Let's take a look at what we have. Let's search for somebody who's a dev lead, because a lot of times different developers are associated with applications. So kubectl get pods minus my selector, and dev lead, I'm going to search for Carissa. So in this scenario, we have 4 applications where we have a dev lead and her name is Carissa. That's great. What if we wanted to do something more complicated, where we want to add multiple labels and search by multiple labels? we can do kubectl get pods -- selector dev lead equals, I'm going to pick Karthik, and then I'm also going to do an env as staging. So we notice in this scenario, out of all the applications that we had, we have one application called homepage staging where we've tagged it with a dev lead of Karthik, and it's running in a specific environment of staging. So this command, kubectl get pod selector with dev lead Karthik, env staging, allows you to add multiple labels and search by multiple labels to filter down the pods that we have running. In our example, we've talked about an application with a label dev lead Karthik in an environment staging. What if we wanted to search for something that was not owned by Karthik? We can do this by adding the not flag. So this becomes dev lead not equals Karthik in the staging environment. The result of this is all of the applications that are not owned by Karthik in the staging environment. In fact, let's look at all the labels associated with it. Dev lead Carissa, Daniel, Jim, Chen, Amy, and marketing. Great. Next up, we want to actually learn how to use the in operator. So we do a kubectl get pods, and instead of -- selector, you can use the -l shortcut. And we're going to look for release versions in, let's say, 1.0 to 2.0. This command will basically look for anything that has a release version that's between 1.0 and 2.0. As we run that, we get a list of different applications or pods that are running that have a release version between 1.0 and 2.0. Show labels to verify that release version 1.0, 2.0. Looks good. What if we wanted to do something that's not in 1.0 or 2.0? Here, we can use the not in operator, and I'm going to use show labels as well. So here we see some applications, catalog dev, for example, that's in a release version of 4.0, 12.0, and so on and so forth. Sometimes we want to also be able to delete by labels. How do we go about doing that? So we have pods, and we have a lot of them, and we might want to delete all of the pods associated with a specific dev lead. So let's take the example of Control-C, -- show labels. Let's pick our favorite dev lead, Karthik, and delete all the pods associated with him. In order to do this, we add kubectl delete pods -l dev-lead equals Karthik. This goes ahead and deletes all of the pods that were associated with a specific dev lead named Karthik. So if we do a show labels again, we'll notice that in our dev lead column, we have some pods, homepage dev, homepage prod, and homepage staging that are in a terminating state that have a dev lead of Karthik associated with them. And if we do this again, there we go. We just have dev leads of everybody except Karthik. So in this scenario, we've deleted all of our pods where their dev lead was Karthik. And there you have it. That's an example of how to use labels to search through your infrastructure. One of the nice things about labels, even though we don't have it in this specific example, is we've used labels with pods in this example. However, you can also use labels with deployments, services, replica sets, etc. So everything I've just shown you can also be transposed to those constructs for services and deployments. Let's figure out how we can add application health checks to our existing Hello World application. Let's pull it up. We can do a cat of Hello World with probes.yaml. And we notice that this is our Hello World. It's still the deployment. In the spec section, we notice with the containers, we have a couple of probes here. We have the readiness probe, and we have the liveness probe. The readiness probe is used to know when a container is ready to start accepting traffic. So we'll give it some amount of initial delay seconds. In this case, we'll do 5. And then we have timeout seconds, which is the amount of time to wait before timing out. We'll use it as 1. In this case, because this is a little web app, we'll use the HTTP GET. The path to probe here will be /. So the endpoint it'll look at is the / endpoint on port 80, which is the same as the container port for which the application is configured. The liveness probe here, we'll use the initial delay seconds of 5 and then timeout of 1, and then do something similar with HTTP GET. Once again, path of / on port 80. So let's go ahead and run this. Clear out of here. Kubectl create -f. Hello world with probes. We'll notice that the deployment was created. Let's take a look at the deployment. It's not quite ready yet because it'll sometimes take a little bit of time to start up the container. Remember how we said wait for 5 seconds before you start up? Let's take a look at this again. And in this case, we see ready 1 of 1. It's up to date. It's also available. Let's make sure the pods are online, as well as the replica sets. So let's take a look at the replica sets first. Desired current ready state all of 1. It's looking good. As well as kubectl get pods. We expect everything to be running, ready state, running with no restarts. All right, it looks good. In this scenario, we configured everything correctly and the application is working as expected. But what happens when we're trying to simulate this in a scenario where things might not work? So we'll pull up another example that I created. Cat, hello world with bad. Let's do readiness first. So in this case, it's the same application as before. And in the readiness probe section, we have an initial delay seconds of 5, timeout of 1, and we're still using an HTTP GET probe on the path of /, but we're looking at port 90. And per the application in this case, it's going to be running on port 80, so this is not actually going to come back. So what happens when we actually run this application? Clear out of here. Kubectl create -f. Hello world with bad readiness probe. So deployment sets is created. Deployments. We notice that it's not in a ready state yet. Let's wait for just a little bit and try this again. We notice once again that the deployment is not quite ready. Age of 17 seconds. If we decide to introspect here a little bit, kubectl get pods, for example, we notice that with the bad readiness probe, this is not in a ready state, but it does show that the pod's running. So if we end up going to describe this pod, actually clear screen. It has some pod pre-information, but what we're really looking for is the events. And here underneath events, we have a warning and it says the reason unhealthy and Kubelet, Minikube, and it says readiness probe failed, the get of HTTP on port 90, and then the error here is, connection refused. So in this case, the readiness probe fails. So as a result, the pod's not actually ready to accept traffic. So that was readiness probes. Let's take a look at liveness probes. So I have an example of cat, hello world, with bad liveness probe. Similar stuff from before. We have liveness probe, initial delay seconds and period seconds, as well as a time of seconds of 1. And we set a failure threshold here. So this is the number of times it'll try to restart until it starts giving up trying to restart the pod and go into a crash loop backup status. So similar scenario, we have a path of /, port of 90, but the container is actually running on port 80. So what happens over here? Kubectl create -f, hello world with bad liveness probe. It's created. Get the deployments. So we notice here that the liveness probe, it looks like it's ready to go. It's in an up-to-date state and it's available. If you look at this again, still ready, but what happens when we take a look at the pods? We notice that the pod's running with the liveness probe in a ready state, but it's restarted once. Now we notice, it's been a little bit of time, so 20 seconds, 30 seconds, 40 seconds. It's restarted again because we have that 5-second threshold. Do this again, we'll notice that it's restarted 3 times. Pretty soon this will start to go into a crash loop backup status. Try this one last time. So we notice here that this has gone to a crash loop backup status and it's not ready anymore. And what happens when we actually describe this pod? Clear screen. Describe PO/bad liveness probe. So we notice here that Kubelet Mini, this is the unhealthy reason, and Minikube liveness probe failed. The get on this endpoint, the dial connection was refused. So as a result, the container with liveness probe failed and it'll be restarted. So we kind of see it in the events for the actual pod. Now, if you look at the deployments as well, deployments, we'll notice that, the liveness probe deployment, which initially it was ready, went into a not ready state and it has 0 available. And we also simulated a bad liveness probe as well as a bad readiness probe too. In this section, we are going to perform an application upgrade, and we're going to upgrade our deployment from one version to another. And later on, we're also going to do a rollback. So let's take a look at the deployment that we are going to initially push. vi hello world black.yaml. Basically, this is similar to the hello world applications we've been deploying so far, but the image name here is hello world black. And we also have a service associated with this, and we're going to call this the navbar service and the navbar deployment. So we're going to do a kubectl create -f hello world black, and I'm going to add this -- record, which basically means that we're going to try and record our rollout history, and that's something I'll talk about in a little bit later. This creates our regular deployment and our service, and to see this up and running in our web browser, we can type minikube service navbar. We've exposed it as a node port, so Minikube can open this navbar service in the web browser. This looks very similar to what we've seen before. We're going to take the navbar and change the color of it in a different deployment. We've already deployed this application, and we have a black colored navbar behind the scenes. We want to update this to a blue navbar, and in order to do that, I already have an image called hello world blue, and I'm going to update that image by doing a kubectl set image deployment. We've called this the navbar deployment. And I'm going to change this to hello world. Well, apparently I can't type, so I'm going to go and actually type this correctly. Deployment. And we see that the image has been updated. Let's take a look at our deployments. See a desired 3, current 4, and available 3. And if you go back to our UI and refresh our UI, there we have it. We've gone from a regular gray background to now what seems to be more of a blue/purple background. So what actually happened here? Let's take a look at our replica sets real quick. kubectl get rs. We notice that we have multiple replica sets here, both associated with the navbar deployment. However, they have 2 different GUIDs associated with them. We notice that this replica set has a desired, current, and ready status, or ready values of 3. And if you look at our pods, we'll also have 3 different pods running for this. Now let's take a look once again at our deployment. CTL. Once again, we have 3, 3, 3, and 3. Basically, behind the scenes, what's happened in this scenario is our deployment, when we redeployed with the new image, we got a new replica set that matches the second set of images that we had, and we had pods re-rolled for that. If we take a look at our rollout history, kubectl, rollout history, for the actual deployment, which was navbar. We'll notice that we have 2 revisions here. First, when we actually created it, and this is our kubectl command that we created with a record of true, and the second revision, which is what we set the image to, we had navbar deployment and we set the image to hello world blue. The reason we initially added the record equals true is to see the actual cause changes that we see in this list. And that's how we do an in-place upgrade. Now what if we wanted to roll back to the first version? That we can do with this specific command. Just like we did a rollout, we can do a rollout undo. kubectl, rollout undo, the deployment name, navbar, deployment. And this will revert our changes back from 2 to 1. So if we look back at our site, there we go. We are back to our first version. A lot of times in this scenario, you might want to actually go back to a specific version. And to that, you can roll out undo, and then you can add a --to revision and add whatever version number you want over here that you saw in the list. Sometimes things don't work as you expect, and you have to take a closer look to debug issues or understand what's going on. There are 3 techniques I use on a day-to-day basis when I work with Kubernetes, so let me show you what these are. Let's look at this example scenario where we have a bad hello world deployment, which has 0 available pods. And running a kubectl get pods command returns the bad pod with 0 pods in ready status with the status of error pull image. What do you do in this scenario? Or how do you debug the situation? If I clear my screen, you can do a kubectl describe deployment, bad hello world deployment. And this gives you the description of the entire deployment. As you can see over here, we have information about the specific deployment, pod template, conditions, replica set information, and under events, it says scaled up replica set bad hello world deployment to 1. So from a deployment perspective, there doesn't seem to be anything going on. Let's look at it from a pod perspective. Clear my screen, kubectl, get pods. Looks like we have a pod in image backup state, so let's introspect on the pod. We can do a describe on the pod, except I have to mention that it's a pod. This returns all the information for the specific pod. There's name information and whatnot. The stuff we're really interested in from a debugging perspective is the events. So as you can see, it was scheduled 5 minutes ago, but it looks like we started to see a warning. But if you look at the type, the very first event that looks a little bit suspicious is this warning, and the reason is failure for Kubelet Minikube, failed to pull image, Karthikeyan unknown pod latest, and we get a specific error associated with that. This gives us some indication that there's actually something going on with the pod with respect to the image. So it forces you to check whether this image is correct or whether you don't have access to the repository that it's sitting in. That's one debugging technique. The other technique that I use a lot is I end up looking at log files for specific pods. So if I do a kubectl get deployments, I have 2 deployments running. Specifically, I'm going to introspect the hello world deployment and look at the pods associated with that. So let me do a get pods for all. So hello world deployment. This is the pod associated with the hello world deployment. I'm going to copy this guy, And I'm going to type kubectl logs, except I don't want the kubectl part. And this command returns all the logs for that specific pod. So in this case, it was a simple web application. So this is the Nginx logs coming out from the pod. That's another technique. The third thing I typically do is sometimes you have to actually exec into the pod to see what's going on. To exec into a pod, we use the kubectl exec command -it. Once again, we need the pod name, so I'm gonna paste that out. Don't need the kubectl logs stuff here. Delete. And we want to pipe this to a specific shell. I can use bin bash and run that. And once we run this command, you'll notice that this says root at hello world deployment and the actual pod name. So we're actually running inside of the pod right now. We can see all the processes in the pod. So we notice there's an Nginx master process, Nginx worker process, etc. And a lot of times you end up having to exec into the pod to make sure that your configuration files are correct, or all the information that you're expecting, environment variables, etc., are actually in the pod that you're looking for. One last thing to talk about is occasionally you might have multiple containers in your pod. So the flag to do that is -c, and in this case our pod name was hello world. And we get dropped back into the same container as we expect. Typically you don't use the -c if you just have a single pod with a single container running in it, but it's useful when you have multiple containers that comprise of the pod. We're going to deploy the PHP guestbook application with a MongoDB database into our cluster. You can find this example in the Kubernetes documentation at the URL below. So let's go ahead into our terminal and try and run this. We're actually going to deploy the guestbook YAML, but before we do that, let's see what's in there. vi guestbook YAML. This file is a lot larger than any of the files we've deployed so far. Seems like it has a deployment of name Mongo, it's linked to a container Mongo 4.2, and then we have a service associated with this, which is named Mongo. You'll notice that there are these 3 dashes, and this 3 dash notation actually allows us to append multiple Kubernetes resources like deployments and services into one single file. So as we go along, we'll notice that we have another deployment. In this case, this is called the front end, has some labels associated with that. And the container that's deployed here is called guestbook with the image of Karthikeyan GB frontend v5. So this looks like this is the actual application or the user interface that we might end up using. And there is a service associated with this deployment named frontend as well. And this is of a type load balancer. So that's the end of the file. So it looks like we have 2 deployments and 2 services that we want to deploy. So let's exit. And let's make sure that we have clean cluster first up. So we'll do a get deployments. No resources found in the default namespace. That's great. As well as kubectl get services. This will just return the Kubernetes service that comes default in Minikube. So we currently have a clean cluster, which is great. So next up, let's go ahead and deploy our application. kubectl create -f guestbook.yaml. So this says that's created a deployment called Mongo, a service Mongo, a deployment front end, and service front end. Let's do a check real quick on the deployments. kubectl get deployments. The front end and Mongo deployments are online. Ready 3 of 3, ready 1 of 1. That looks good. Let's take a look at our services. kubectl get services. We now have 3 services here, the front-end service, the Mongo service, and the Kubernetes service, and front-end of type load balancer. Great, it looks like everything's online. Let's see if we can actually access the web interface. In order to do that, we can do a Minikube service front end. And this creates the tunnel, and we have the guestbook application up and running here. How do you pronounce Kubectl or Kubectl, for example? Great. So there we have it. This is a larger application than we deployed in the past, which involves multiple deployments and services, and we have it up and running in the Kubernetes cluster, as well as the interface that we see over here. The Kubernetes dashboard is a simple web user interface for Kubernetes clusters. It allows users to manage and troubleshoot applications running in the cluster, as well as manage the cluster itself. One of the most common asks in the container world is for the need for a UI to visualize what's going on with the cluster. It was one of the most requested features of Docker when it first started, and is a common requirement for DevOps engineers to manage clusters. Kubernetes learned this lesson early on and created the Kubernetes dashboard for this very purpose, and it allows you to monitor and view clusters from an operational perspective. So let's go ahead and see how we can run this in Minikube. Let's make sure Minikube is up and running. To do this, I can do a Minikube status, and Kubelet and API server, everything seems to be running. One thing I like about Minikube are the add-ons, and the Kubernetes dashboard actually comes bundled as an add-on inside of Minikube. So let's take a look at the add-ons. So if I do a Minikube add-ons list, we'll notice that there are a bunch of different add-ons inside of Minikube that are already bundled. So in here, we'll notice the dashboard that is in a disabled state. So let's go ahead and enable that. Clear my screen. Minikube add-ons enable dashboard. It says that the dashboard is enabled, but it also says some dashboard features require the metric server add-on. To enable all the features, please run Minikube add-ons enable metric server. So this is just telling us that we want to enable the metric server add-on in order to get CPU and memory information that's also shown in the dashboard. So let's go ahead and do that. So I'll do a copy of that. Minikube add-ons enable metric server. And this says that the metric server's add-on is enabled. So let's look at our add-on list again. Minikube add-ons list. So now we see here that the dashboard is enabled, as well as the metric server. Great, seems like things are online. So let's run the dashboard. To start it up, I can type Minikube dashboard, and this will pull up the dashboard in my web browser. We notice at first that we see the CPU usage and the memory usage, and this is actually given to us by the metric server that we just enabled. We'll notice at the very top, we have a thing called default. This is actually all of the different namespaces that we have in the cluster, and by default, the dashboard will show you everything in the default namespace. But we can also change this to look at all the different namespaces as well. So in our entire cluster, we have workload statuses for the daemon sets, deployments, pods, replica sets, etc. I'm going to flip this back to the default cluster. And here we have information about the deployments that we had. So from the last chapter, we had the front end and the MongoDB deployment. We still have those existing. They were created 26 minutes ago. Shows us the images, etc. You can get a sense of all the different workloads like the pods. We can get information about the replica sets, etc. And you'll notice that the information up here with the CPU and the memory usage changes depending on what we're actually looking at. Next up, we have the services. So the different services running in the default namespace. And any kind of configuration. So if you want to look at the different config maps that you have in your cluster or in your namespace or secrets, etc., you can kind of take a look at them over there. Information about the cluster, such as the role bindings and roles, etc. And also the CRD definitions as well. One quick thing I really like is the little search functionality that we have up top. So I can search for front end, etc. And anytime there's a deployment or a pod associated with the name front end, we can see that. So let's actually hop into a deployment. There are a couple of things here I want to touch on. So one thing I find myself doing every now and then is for a specific deployment, if I don't want to muck with the YAML, I can actually edit the different resources in here as well. So I can hit this edit resource button, and this shows us the YAML for the deployment. And it shows us all of the information associated with the deployment. So if for some reason I wanted to add a different label, for example, so I can do an app.kubernetes.io/custom label, and I'll just call this hello as the value, and I can do an update. This action is equivalent to running the kubectl apply command for the specific spec, but I'm going to do that. And here in just a second, we'll notice that we ended up adding the custom label. So custom label hello. And the other thing you might end up using this for is to change the number of replicas. So by default, this replica had, or this deployment had 3 replicas, and you can change that to 2 or more. Let's bump this up to 4, and we can do a scale. And once again, the command associated with this is kubectl scale -n, the deployment name front end, and then set the replicas to 4. So once again, in the under pod status, we saw that change from 3 to 4, and we don't have any old replica sets, etc. The other thing you might use the dashboard for is to actually look at events. So any events associated with the deployment is shown here in the events. And let's look at pods real quick as well. There's a couple of things in pods that end up making this really useful. I'm going to pick an arbitrary pod. So I'm going to pick the front end pod. And a couple of things that are useful with the pod specifically are you can view logs, you can exec into a pod, and also change resources in the pod like we could do for deployments. So let's look at the logs for this pod. So instead of doing a kubectl logs command, you can look at the logs directly for the specific pod. As well as if you try and exec into the pod, we do get a shell inside of the guestbook for the specific pod itself. So you can do an ls-al, for example, and this is execing into the pod and showing you what's running inside of the pod. One last thing I want to show you in the dashboard is that you can actually create resources from the dashboard itself. It's not a feature that a lot of folks use that much, but it's still really useful. In order to do that, you can click the create new resource icon from the top, the little plus sign. Click that, and we have 3 options here. You can create from input, where you can enter your existing YAML or JSON content. You can create from a file, where you can paste a specific file, or you can create from a form. For ease of use, I'm just going to create something from the form. So let's give this an app name. I'm going to call it Hello World. A container image. So I'll use my Karthikeyan Hello World latest. And let's say I'll do 4 pods, and I don't really need a service for this. So I'm going to hit deploy. And we'll notice that we went back to the main screen. There's the K8s app. There's a deployment that's not online, so you'll notice that there's 0 4 pods available just yet. If we give this a little bit of time, we'll notice that everything turned green, as well as 4 pods available, and we're back in a happy state. So there you have it. I'm going to go into the dashboard, or rather go into this deployment. Everything seems to be running as expected, and we actually created this Hello World deployment from the dashboard itself. So this is just a quick overview of the Kubernetes dashboard. Gives you a quick look and feel of what the dashboard is and what it does. Applications require a way for us to pass data to them that can be changed at deploy time. Examples of this might be log levels or URLs of external systems that the application might need at startup time. Instead of hard-coding these values, we use config maps in Kubernetes to pass these values as environment variables to the container. For example, in this scenario, I have a deployment where I have a container called Karthikeyan reader, and as an environment variable, I want to pass log level of error. So if I run this, kubectl create -f reader deployment.yaml, I will see the deployment's been created. get pods. I see that the pod is in a container creating status, and we see that the pod is running. Let's take a look at the logs. Need the pod name first. We'll notice that this says that the log level passed via an environment variable was error, as per the application. What we'd like to do is we'd like to change this at deployment time. For this, we can use something called config maps. In order to create a config map, we can use the kubectl command, kubectl create config map. We're going to call the config map logger, and we are going to take this from literal, and we're going to call the actual value log_level equals debug. This means that we are going to pass something called log_level equals debug to the actual container as an environment variable. We get config map created, and let's take a look at the YAML for the deployment and how that's going to change when we use config map. We will use vi for this. This is vi reader config map deployment.yaml. Open this up. And this is similar to the last example that we opened up, except you'll notice that we have an environment variable named log level, but the values are value from config map ref and the name of the config map. And the key for this is the log_level. So this structure basically takes a config map, which is called logger, and reads the key called log level out of the config map. So let's go ahead and run this example. While this deployment is being created, let's take a look at the actual config maps that we have created. We can do this by doing a kubectl get config maps. As we notice, we have the logger that we've created from before, and we can actually introspect into this guy by doing a kubectl get config map /logger -o YAML, similar to the way we look up deployments. And this returns the entire config map to us, and you'll notice that in the data section, there's a log_level equals debug, which is what we had initially set it to. By now, our deployment should be up and running. Let's verify this by doing a kubectl get deployments. And let's take a quick look at the log for this guy. kubectl logs. Except I cannot do a logs on a deployment. I'd have to do this on the pod. Get pods. I want the dynamic one. And there we see it. The log level passed via environment variables was debugged. And that's how you use config maps to send dynamic values into your deployment. Just like configuration data, applications might also require other data that is more sensitive in nature. For example, like in this scenario, database passwords or API tokens. Passing these straight in YAML for a deployment or pod would make them visible to everyone. In cases like these, we'd want to use something called a secret. Let's see what that is. In order to create a secret, we can do a kubectl create secret. We want to create a generic secret, and let's call it an API key. We're going to pass this from literal, and we'll call it API_key equals something like that. In this scenario, we've created the secret. So let's take a look at our secrets API. And we see a secret of name API key type opaque, some data in it. If you want to take a look at the actual secret, you can do a kubectl get secret, and we call this API key. And if we try and do an O YAML, we'll notice that the data portion has the API key, but we have a different value from what we had initially typed. That is because this value is encoded in a base64 format. Now, how do you actually use these secrets with an application? We have an example application in our exercise files called secret reader. Looking at that, this is very similar to using a config map, but instead of config map ref, we use secret ref. We called our secret API key, so we pass that as the name, and the actual key in that was called API_key. So let's deploy this guy. CTL, create. The deployment for the secret reader has been created. Let's see if our pods are running. The pod is running. I'm going to copy this and look inside the pod. The pod in this instance is just printing out the value passed to it via an environment variable, but the value is hidden behind a secret and is protected from the casual observer. Jobs are a construct that run a pod once and then stop. However, unlike pods and deployments, the output of the job is kept around until you decide to remove it. In this example, I'm showing you simple job.yaml, we have the template, and we have a spec. In the spec, we have containers. It's just a busybox image that is running a loop from 9 through 1 and just echoing it out at the end. So let's go ahead and run this guy. kubectl, create -f, simple job.yaml. It says the job was created, so let's introspect. kubectl get jobs. We'll notice that the final countdown job has 1 of 1 completion, duration 2 seconds, and age of 7 seconds. So if we do a kubectl get pods, for example, we'll notice that we have the final countdown pod with some metadata over there. It's not in a ready state, but the status of that was completed. We can actually even take a look at the logs for this. So we can do kubectl logs and then the pod name. And you'll notice that we get the output from 9 through 1, just like what we had in the code. Now, let's take a look at crons. So crons are like jobs, however, they can run periodically. So I have a cron here, it's called cronjob.yaml. It's still similar to what we had before. All it's doing here is printing out the date and then echoing hello from your Kubernetes cluster. Restart policy on failure, and so this also has a schedule. In this case, it runs every minute. So let's go ahead and run this. kubectl create -f cron job YAML. So let's look at the job for this. We can do a get cron job. And in the example here, we're seeing hello cron on the schedule with suspend as false. This just means that don't ever suspend it, just always keep running it. It's not active right now, and it hadn't been scheduled yet, so let's look at it again. So there's active of 1, last scheduled 9 seconds ago, age of 29 seconds. And in fact, if you even look at the jobs for this, we'll notice that hello cron actually ran for 3 seconds about 23 seconds ago. So if you wait a little bit and then try again, let's see, kubectl get jobs. Here we notice that it's been a little over a minute and a second hello cron just ran. And if you look at the cron job as well, nothing active right now, last scheduled for 32 seconds ago, in the same suspend status of false. One thing that comes up a lot with cron job specifically is how do you pause it or stop this? Let's clear my screen. Actually do a quick kubectl get cron jobs. The name of that was hello cron, so we can actually go ahead and edit this. kubectl edit cron job / cron. This is the actual cron job. And later down here, we'll notice that the suspend status is false. So I'm going to actually change this to true. Exit out. And if I look at the cron job again, we'll notice that the suspend status is true. And then I'm going to give this a little bit of time and then I'm going to check again to see when the last schedule was. Typically, we have this on a 1 minute schedule. So, if we wait a little bit over a minute, we'll start to notice that the last schedule would have happened, 1 minute and 23 seconds ago, etc. So something over 60 is what we're looking for. All right, let's try it out. Notice that, the last schedule was still 82 seconds ago and suspense is still true. And if you get to look at the jobs as well, we still have the age of the last one that actually ran was 92 seconds ago. So that's how you stop a cron job. A daemon set ensures that all nodes run a copy of a specific pod. As nodes are added to the cluster, pods are added to them as well. An example of a daemon set would be running your logging or monitoring agent on all of your nodes. In this example, I'm going to use a simple busybox container and deploy it as a daemon set. This is my YAML for the daemon set. As you can see, it's a kind of daemon set with a spec of example daemon set. Specifically, it's an image busybox. Let's go ahead and deploy this. We deploy this by the kubectl create -f daemon set.yaml command. Pretty similar to how we've done other deployments before. To fetch them, we can do a kubectl get daemon sets. We notice that we have the example daemon set up and running, and it's desired, current, ready, up to date, and available. You'll also notice this node selector, which I'll get into in a second. If we look at our pods, you'll notice that we have a pod running. Great! The daemon set is working as expected. This is not something new that we haven't seen before. Let's see how we can get daemon sets to work on specific pods. Let's go into our editor, vi, daemon set, and let's pull up infrastructure development. In this file, we'll notice that we have another daemon set. We just called it example2, and we add a specific label to this called a node selector, and we add the label infra of development. Back on Minikube, I do a kubectl get nodes, and I show labels. I'll notice that Minikube has some labels. One of these labels that I've added is infra of development. So if I deploy this daemon set, clear my screen, kubectl create -f daemon set infra development, it will create the daemon set. Let's explore. Kubectl get daemon sets. You'll notice that in daemon set 2, we have a node selector with label name infra and value development. We also had a node for Minikube with the label name infra and value of development, which is why we notice that the daemon set is actually up and running. So let's take a look at our prod daemon set. vi daemon set infra prod. You'll notice that this matches a prod daemon set, that's what we've called it, and under node selectors, we have the label with the key infra with the value of production. So let's deploy this. Kubectl create -f daemon set infra prod. Well, our daemon set was created, but let's take a look if it's actually up and running. Kubectl get daemon sets, and we notice that we have the example daemon set 2, where we have infra equals development, and we have the prod daemon set, where we have desired, current, ready, up to date, and available of all zeros, because we do not have any infrastructure nodes of type production. All the nodes that we have right now are all development. And we know this because if we do a kubectl get nodes, show labels, we have a single node called Minikube with labels And we have a label of infra. However, there's no values other than development. Next up, I want to take a look at stateful sets. I have a VI stateful set. And we're going to do a quick example with Zookeeper. Stateful sets manage the deployment and scaling for a set of pods and provide guarantees about the ordering and the uniqueness of these pods. But unlike a deployment, a stateful set manages the sticky identity for each of these pods. So let's take a look in this example. So we have a service of ZK. I'm going to use Zookeeper for this example. And we have an API, and it's of a kind stateful set. In this case, we have affinity associated with it. And finally, we have the container. It's a Kubernetes Zookeeper. And we have the command that it runs, which is a little bit hairy, but the idea of this is to understand how this runs. If you're not already familiar, Zookeeper is just a simple key value store that's commonly used. It's Apache Zookeeper if you want to take a look, right? So we have the stateful set, and I'm going to deploy this by doing kubectl create -f. And I have my service and my stateful set created. To take a look at the stateful set up and running, kubectl get. And we see that we have the stateful set, which is called ZK, with a specific age. Let's make sure that the pods for this are also online. We have the daemon sets pods running, but we're going to ignore those. And we also have the ZK0 pod that's up and running as well for the last 32 seconds. So this is a simple example of a stateful set. Typically, you would end up having multiples of these running on different nodes, but we're just showing a simple example of a single stateful set running on Minikube. One of the most common questions that people ask is, how do I deploy Kubernetes to production? Previously, it was difficult to deploy Kubernetes to a production environment. In the container community, it was well known that Kubernetes is a great tool, but at the time was almost impossible to deploy and manage. Fortunately, with the growth of Kubernetes and its community, a lot of work has been performed in this space, and it's much easier to deploy Kubernetes today. So let's take a look at some of the most common ways to install Kubernetes. The most common way to install Kubernetes today is using the kubeadmin tool, also known as kubeadm. This is probably the easiest way to install it on any public cloud, private cloud, or on-premise infrastructure. Essentially, you're required to initially provision the master host with Docker and the Kubernetes distribution you're looking for. Once this is done, you can run kubeadmin init, which starts up kubeadmin and provisions the control plane. Once completed, kubeadmin will provide you with a token called a join token. On each of your worker nodes, you can simply run the kubeadmin join command with your join token, and the workers will join your cluster. Once the nodes have joined, you'll need to install a pod network for your pods to be able to communicate with each other. There are many different networking solutions that you can implement, which have different pros and cons depending on your infrastructure needs. However, Flannel and WeaveNet are a great place to start. Kops. If you're working in an AWS infrastructure and you're wanting to install a cluster, then Kops is the tool for you. Kops has a number of useful features. It automates the Kubernetes cluster provisioning in AWS. It deploys highly available masters, also known as HA. It permits upgrading with kubeup, uses a state sync model for dry runs and automatic idempotency. It generates configuration files for AWS CloudFormation and Terraform configuration, supports custom add-ons, and finally, uses a manifest-based API configuration. Kops is a very popular way to deploy Kubernetes on AWS and looks very similar to the way kubectl operates. If you're going to run Kubernetes on a cloud provider like AWS, Azure, Google, or Oracle Cloud, you might want to consider one of their native container services like Amazon Elastic Kubernetes Service on AWS, Azure Container Service for Azure, Google Container Engine for Google Cloud, or Oracle Container Engine for Kubernetes on Oracle Cloud. Now, you might ask, why am I wasting time using kubeadmin or Kops when I can just use a managed service? This is a really good question. For those folks working in the cloud, managed Kubernetes services have become very popular. you spend a lot less time managing the Kubernetes control plane and spend more time on your applications deployed in your data plane. However, providers don't let you configure all the different elements of Kubernetes that you may need and might trail the latest Kubernetes version as well. So my recommendation is this. If you're running Kubernetes in the cloud, start with a managed Kubernetes service because it reduces overhead of managing the Kubernetes control plane. If you realize that there are other Kubernetes features your applications might require that are not provided by the managed service, then perhaps roll your own installation. If the managed service fits your use case, I'd highly recommend using it versus rolling your own. Namespaces are a fundamental concept to add multi-tenancy to your Kubernetes instance. Kubernetes provides multiple virtual clusters backed by the same physical cluster. These virtual clusters are called namespaces. There are 4 primary use cases. 1. Roles and responsibilities in an enterprise. 2. Partitioning landscapes. For example, dev versus test versus production. 3. Customer partitioning for non-multi-tenant scenarios. For example, if you're a consulting company and you have multiple customers, you can use this feature. And finally, for application partitioning as well. First, let's talk about the use case related to roles and responsibilities in an enterprise. Enterprises have many teams that typically operate independently of each other and might have some shared interfaces and APIs to communicate with each other. The use of namespaces is perfect in this scenario because teams are able to operate independently without stepping on each other. Namespaces also prevent them from confusing services and deployments that might not belong to them. Here are a couple of things you'll need to watch out for. Plan in advance how you want to manage your enterprise in a Kubernetes environment. Setting standards up front will help you in the long term with infrastructure management. Don't simply transpose existing on-premise controls and procedures to the new environment. This might result in bringing your existing infrastructure baggage to the new environment, which is supposed to be more agile. Another common pattern is using namespaces for dev, test, and production environments. With most teams building a continuous integration or CI pipelines, you can easily define CI pipelines to deploy an entire environment in a quick and easy fashion. Some anti-patterns to watch out here for are, sometimes you will end up with a really large namespace because you have many applications that are running. In these scenarios, it might be good to create additional namespaces for groups of applications. For example, e-commerce dev namespace for all e-commerce related applications. Another scenario is you might end up with too many environments. Just because you can does not mean that you should. Don't abuse the feature because it will result in too many unnecessary environments. If you don't use a staging deployment or you don't use a staging namespace, then don't create one. Consulting companies and small software vendors might use this method a lot. You could create a namespace for each customer or project to keep them distinct while not needing to worry about reusing the same names or resources across different projects. A new side effect of using the Helm package manager introduced by Kubernetes is that K8s applications, which are typically comprised of deployments, services, etc., have gotten very complex. And when installing these applications, they are delivered in their own namespace, which makes it easier to encapsulate the application in one single spot in your Kubernetes cluster, all in just a single namespace. When you're done using the application, you can just delete the namespace. Interacting with namespaces is very straightforward. Let's discuss the basic commands related to them. To just get all your existing namespaces, you can just do a kubectl get namespaces. To create one, all you have to do is do a kubectl create namespace followed by the name you want to use. Similarly, to delete the namespace, it's a kubectl delete namespace followed by the namespace you'd like to delete. When deploying a specific resource, like a deployment to a specific namespace, just add the -n namespace name, and the resource will exist in that specific namespace. Once your infrastructure and your application have been deployed successfully, you run into your next challenge. Are they operating correctly? Have there been any errors? Are they even online? The DevOps practices of monitoring and logging help you answer these questions. Let's take a look at how to do this specifically from a Kubernetes perspective. From a Kubernetes perspective, starting out, it's better for your applications running in a pod to write to standard out. This is because Kubernetes will automatically pick up the logs and show you anything in the log info when you use the command kubectl logs to fetch the logs. This is really useful when you're doing development. Once your application is running in staging or production, you might consider using a logging platform like Elasticsearch and Kibana with logs being shipped to it from pods using Fluentd, Filebeats, or Logstash. The architecture of this paradigm is shown here. You would typically run a deployment for your Elasticsearch and Kibana instance outside of your application. The Elasticsearch endpoint needs to be accessible to pods in the cluster, and the Kibana instance should be exposed as a service so that you can see log information in the Kibana user interface. Then, in your application deployment, you'll want the log shipper, Fluentd, Logstash, or Filebeats, to gather log data and periodically send it to the Elasticsearch instance. From a monitoring perspective, we have a few things we'd like to monitor: the node health, the health of the Kubernetes cluster, and application health and metrics. For node and Kubernetes health, the combination of two open source projects, cAdvisor and Prometheus, give an elegant way to monitor your cluster and applications. cAdvisor is an open source resource usage collector that was built for containers. It auto-discovers all containers in a given node and collects CPU, memory, file system, and network usage statistics. cAdvisor also provides the overall machine usage by analyzing the root container on the machine. The other project you really want to look at is called Prometheus. Prometheus is an open source system monitoring and alerting toolkit with a query language that works really well for application-specific metrics and can also be used from an alerting standpoint. Prometheus was initially used to collect application metrics, like number of successful logins per hour, but can also be used natively to monitor Kubernetes itself with projects like kubeprometheus. You can instrument your application to save application monitoring data at a /metrics endpoint that Prometheus queries in a timely manner. Prometheus and Advisor are typically linked to Grafana, which is an open source tool to visualize monitoring data. Authentication and authorization are two of the most common topics that arise when folks are trying to integrate Kubernetes into their infrastructure. In this section, I'll go over what these features are and give you a working understanding of how authentication and authorization work. From an architecture perspective, users who are trying to access the Kubernetes API via the kubectl command first have to be authenticated to access the API, and then authorized to run specific actions. Occasionally, users will also need to have admission control to approve or reject a request. First off, we need to understand what a user means from a Kubernetes context. There are actually two kinds of users: normal users, like you and me, and service accounts, which are internal users to the system. We typically think of normal users as users who are in an LDAP or an SSO system in our enterprises. From a Kubernetes perspective, these users are managed outside of Kubernetes. Service accounts are managed by the Kube API server, bound to a specific namespace, and tied to credentials managed in secrets. There are four pieces of information that define a user: the username, which is basically a string, a UID or a unique ID, which is an identifier that is more consistent and unique than the username, a group, which is a string that associates users with a set of commonly grouped users. These are used later on by the authorization model, and extra fields, which is basically a map of strings that holds additional information used by the authorization system. Authentication in Kubernetes defines whether a user has access to communicate with a Kube API server, and authorization defines whether a user has actual permissions to perform specific actions. There are a number of ways you can authenticate. The entire list can be found in the Kubernetes documentation, but we'll look at the four most popular modules that enterprises use today: client certs, static tokens, OpenID Connect, or the webhook mode. Client cert authentication is enabled by passing the client CA file option to the API server. The reference file must contain certificate authorities to validate client certificates passed to the API server. If a client cert is presented and verified, the common name of the client certificate is used as the username for the request. This is a straightforward way to manage Kubernetes if you're comfortable with handling certificate managements in your org. The API server reads the bearer tokens from a file when given the --token auth file option on the command line. The token auth file is a CSV file with 4 columns: token, username, user UID, followed by optional group names as shown in the example. The caveat to this method is that these tokens last indefinitely and you're required to restart the API server for any changes in tokens to take place. The static password file is similar to this method, but the values are passed as basic auth parameters. The benefit of this method is that it's very simple and easy to manage a small batch of users this way. For larger organizations that already have OAuth, such as Google or Azure Active Directory, you can configure the OpenID Connect tokens to authenticate against Kubernetes. The details of this are complex, and I'd recommend reading the docs for this method. And finally, there's authentication using webhook tokens. This is one of the most common methods that's used by a number of organizations who want to have their users interacting with Kubernetes, but also manage tokens in an easier way. Using this method, the Kube API server makes a request to an API that's defined by you to authenticate. The remote API decides whether a token passed to it is a valid token or not, and then responds back to the server. On the authorization front, there are 3 common ways to perform authorizations: ABAC, RBAC, or webhook. Let's see what these are. ABAC, or Attribute-Based Access Control, defines an access control paradigm whereby access rights are granted to users through the use of policies that combine attributes together. The ABAC file defines what access a specific user might have to all resources. In the example config shown, Karthik has master access to all attributes, whereas the user Carissa only has read access to all the repos and namespaces. RBAC is role-based access control. This is the most common authorization mechanism used in Kubernetes, and a lot of applications end up using RBAC to authorize their service accounts. I would recommend that you turn on this functionality on your Kube API server, even if you're using another authorization mechanism, because you'll end up using something that will require RBAC being installed. RBAC depends on roles and cluster roles. These are rules that represent a set of permissions. A role can be defined within a namespace with a role, or cluster-wide with a cluster role. In this example, we see that a role is in the default namespace that allows read access to all pods. Role bindings grant permissions defined in a role to users. They hold the users or group as a reference to the role being granted. Permissions can then be granted within a namespace with a role binding, or cluster-wide with a cluster role binding. The webhook mode for authorization, like the authentication webhook mode, allows you to define what permissions are allowed for a specified user. The Kube API server will send a request with the user and resource attribute data to a remote server that you define that interprets the request and defines whether a request is allowed or not. This method works really well if you're trying to integrate with a third-party authorization system, or if you want a complex set of rules.